You are welcome to my YouTube channel. Our topic today is elementary set theory. We will begin by defining a set. A set is a collection of objects. It is a well-defined collection of distinct objects. For an example, the set A, which contains chair, table, stool, and sofa, is a set of 4 objects. The objects inside the sets are called elements. Please note that identical elements count once in a set, and order is not important, meaning that anyone that comes first, it doesn't really matter. Sets are usually denoted by capital letters, for example A, B, C, and the elements of the set are actually denoted by small letters, just like X, Y, Z. We define a particular set by writing its element in enclosed curly brackets. Now, a set containing nothing is called an empty set and is usually denoted by 2 braces or the notation for an empty set. Now, if A is an element of a set A, we write A to mean an element of X with that notation that looks like E but turned in the reverse direction, and it reads as A is an element of X. And if A is not an element of X, it is also written with that notation. Let's look at a very simple example. If I have a set of integers, everybody knows that 1 is an element of an integer, but 3/2 is not an integer. So this is how we denote them. We can also define a particular set by stating properties which its element must satisfy. For example, let B be the set of numbers from 1 to 7. We use the variable X to represent an arbitrary element and write B to be equal to X, such that X is a set of natural numbers ranging from 1 to 7. Now, this is called the set builder or predictive form of set representation. Here, you can either use the 2 dots or you use a straight stroke to mean such that. That is the meaning of that 2 dots in the set there. Another important tool in set theory is what is called the Venn diagram. The Venn diagrams are pictorial illustrations of sets and their operations. With an outer square representing the universal set and inner circle representing the set, we can show the operations of a set. Venn diagrams were actually created by John Venn in 1880. Now, this is what we mean by Venn diagrams. Sometimes you may be asked to shade part of the Venn diagram. For example, the universal set. We shade everything. The 2 rings there are used to represent the set, while the rectangular box is used to enclose it. That is what we call the Venn diagram. Now, if you're asked to shade A union B, that is how we shade it in the second example. You may also be asked to shade A intersection B or A complement. This is how we represent them. You can be asked to shade A difference B, or which is equivalent to A intersection B complement. That is how we shade it. You may also be required to shade A intersection B complement, which is equivalent to A complement union B complement. This is how we shade them. See, we have so many representations here, A union B complement and B complement. We also have an extended form of the Venn diagram, the one that has 3 circles in it. This is how we shade A intersection B intersection C. This is how we shade their union of A, B, and C. This is how we shade A intersection B complement intersection C. This is how we shade A complement intersection B complement intersection C. Let's look at some applications of Venn diagram. In a recent survey of 400 students in a federal university, Lokoja, 100 students are listed as smokers, 150 students as chewers of gum, 75 students were listed as both smokers and gum chewers. Find out how many students are neither smokers nor gum chewers. Solution: let Mo be the set of students in question, the universal set be the set of students questions, and let A be the set of smokers, then B be the set of gum chewers. Then the number of the universal set is 400. The number of A is 100. The number of B is 150. While their intersection is 75. We want to find the value of A complement intersection B complement. Now, using the Morgan's law, the Morgan's law says A complement intersection B complement is equal to the universal set minus set A union B. And when you substitute the values there, you're going to have 400 minus 100 minus 150 plus 75, giving us 225. Therefore, 225 students are neither smokers nor gum chewers. Another example where you can apply the Venn diagram. A factory inspector examined the defects in hardness, finish, and dimensions of an item. After examining 100 items, he gave the following reports: that all 3 defects, there are 5 items there, then defects in hardness and finish are 10. The ones that have defects in dimension and hardness are 20, while defects in dimension and finishing is 8. Defects in finishing only is 30. Defects in hardness only is 23, and defects in dimension only is 50. After giving this report, the inspector was fired. The question now is, why was he fired? Okay, let's go through what the inspector actually wrote. Now let's represent H with hardness, F with finishing, and D with dimensions. I had to draw a Venn diagram to represent the information given. This is how the information will be represented in a Venn diagram. Now let's do some calculations. Based on the information given to us by the inspector, the number of H intersection F intersection D is 5. The number of H intersection F is 10. D intersection F is 8. D intersection H is 20. Number of F is 30. Number of H is 23. Number of D is 50. This is given information. Now you apply the Morgan's law again to get the number of H union F union D. And when you do the substitutions properly, you're going to get to 70. However, D union F alone will give us 72. And that is where the problem now is. If H union D union F gave us 70, and only 2 items alone is giving us 72, it means that there's a problem somewhere. It means there's a problem somewhere. So that is why At the conclusion, you will see that the inspector's report, which says that 72 is less than 70, is actually unrealistic. Hence, he was fired, meaning he didn't give a proper report. Thank you for watching. Bye.